The winter of 1881 arrived in the Appalachian highlands of eastern Tennessee with the kind of cold that settled into the bones of the mountains and refused to leave. Samuel Greer noticed it first in the woodpile. By the third week of December, he had burned through a full cord of split oak, and the temperature inside his cabin had not once risen above 48 degrees Fahrenheit after midnight. The stove was adequate for cooking and for warming a narrow circle of air around itself. It was not adequate for the cabin. It had never been adequate for the cabin. No one stove in that hollow was adequate for the cabin. His property sat at 2,800 feet elevation on the western slope of a ridge that channeled the northwest wind directly down the hollow every night from November through March. The wind did not blow hard. It simply moved, steady and relentless, pressing against the log walls of every cabin in the settlement and drawing heat out through every gap, every poorly fitted window frame, every place where the chinking had dried and pulled back from the logs over the summer. The settlers of Greer's Hollow, named for Samuel's grandfather, who had been the first to clear land there in 1821, had lived with this cold for 3 generations. They managed it the same way every generation before them had managed it. They burned wood. More wood than they wanted to burn. More wood than they could easily afford. The wood problem in the Appalachian highlands of 1881 was not a shortage of trees. The ridges above the hollow were covered with white oak, hickory, tulip poplar, and chestnut in densities that would take generations to clear. The problem was labor. Every cord of firewood required felling, bucking, splitting, hauling, and stacking, work measured in days per cord and cords per winter. A family of 4 in a standard 16 by 20 foot cabin at that elevation burned between 6 and 8 cords of wood from October through April. That represented between 12 and 16 full working days of labor just to cut and process the fuel before a single piece was burned. Added to spring planting, summer cultivation, autumn harvest, livestock management, and the 100 other tasks of subsistence farming, the wood requirement consumed a portion of the family's total labor budget that left almost no margin for anything else. Samuel Greer was 34 years old in the winter of 1881 and had a wife named Ruth, 3 children aged 4, 7, and 11, and a left hand that had been partially disabled since a logging accident in 1878 had severed 2 tendons in his palm. He could still work, and he did, but the sustained axe work required to cut and split 7 cords of firewood each autumn caused him pain that built through October into a grinding daily companion by December. He said nothing about it to Ruth, and nothing about it to his neighbors. He split wood every morning before breakfast and stacked it in the shed and said nothing. What he did instead was read. Samuel Greer was one of perhaps 4 men in Greer's Hollow who read with any regularity, and he read everything he could access. The county library in the nearest town 14 miles away received a modest collection of agricultural and scientific periodicals, and Samuel borrowed whatever he could carry on his monthly supply trips. In the autumn of 1880, he had read a brief article in an agricultural journal about heating experiments being conducted in Europe, specifically in France and Germany, where engineers and farmers were testing the use of buried clay pipes to draw outdoor air through the earth before introducing it into buildings. The earth, at sufficient depth, maintained a constant, moderate temperature. Air drawn through pipes, buried at that depth, arrived at the building warmer than outside air in winter and cooler than outside air in summer. The system required no fuel. It required no maintenance beyond the initial construction. It simply used the thermal mass of the earth itself as a heat exchanger. Samuel had read the article 3 times and then sat looking at the wall of his cabin for a long time. The principle the French and German engineers were testing in 1880 was not new. It was a formalization of something that people living close to the earth had understood intuitively for centuries. Caves maintained comfortable temperatures year-round because the rock surrounding them held the Earth's deep temperature, regardless of surface conditions. Root cellars stayed frost-free through the harshest winters for the same reason. The thermal mass of the Earth at depth was a stable reservoir of moderate temperature that surface weather simply could not reach. What the European researchers had done was apply this principle systematically to above-ground habitation. If you buried a pipe deep enough in the earth, the pipe walls would absorb the Earth's stable temperature. Air passing through that pipe would exchange heat with the surrounding Earth, arriving at the outlet end at a temperature closer to the Earth's deep temperature than to the outside air temperature. In winter, outside air at 5 degrees Fahrenheit entering a 40-foot buried pipe at a depth of 6 feet would exit the pipe at approximately 38 to 42 degrees Fahrenheit, depending on pipe diameter, airflow rate, and soil conditions. Not warm enough on its own to heat a cabin, but dramatically warmer than the outside air infiltrating through every crack and gap in a conventional log structure. The secondary principle involved the air infiltration problem that every log cabin faced. A conventional cabin leaked. Cold outside air entered through every gap in the walls, around door frames, through window joints, under the floor. This infiltration was not a small problem. On a windy night, it amounted to multiple complete air changes per hour, meaning the entire volume of air inside the cabin was replaced by cold outside air several times every hour. All the heat the stove produced went directly into warming this infiltrating air, which immediately leaked back out and was replaced by more cold air. The stove was not heating the cabin. It was heating an endless supply of cold outside air that passed through the cabin and left. The earth tube system addressed both problems simultaneously. By providing a controlled, intentional inlet for outside air that had been pre-warmed by the earth, and by sealing all other infiltration points to force air to enter only through the pipe, the system transformed the air exchange from a liability into an asset. Instead of raw 5-degree air infiltrating randomly through dozens of gaps, 40-degree air entered through a single controlled point. The heating load dropped dramatically. The stove that had been fighting a losing battle against random cold air infiltration now had to raise air temperature by 30 degrees instead of 65 degrees to reach comfortable interior conditions. Samuel Greer had understood this in theory since reading the journal article. The question that occupied him through the autumn of 1880 and into the winter of 1881 was whether the materials available in a Tennessee highland hollow could replicate what French engineers had built with manufactured clay pipe, lime mortar, and precision-cut stone intake chambers. He had none of those things. He had creek clay, fieldstone, the hollow logs that settlers use for water pipes, and a mountainside with a 6-foot deep frost line. He believed it was enough. Samuel raised the idea carefully. He was not a man who liked public ridicule, and he had enough experience with the Hollow's community gatherings to know that unusual ideas received a specific kind of reception there. He mentioned it first to his closest neighbor, James Alcott, whose property sat 300 yards up the hollow, and who was generally the most thoughtful man in the settlement. Alcott listened to the explanation without interrupting, which Samuel took as a good sign. When Samuel finished, Alcott was quiet for a moment. "So you're saying you want to suck cold air in through a hole in the ground and somehow that makes your cabin warm," Alcott said. "The earth warms the air before it gets to the cabin," Samuel said. "The earth," Alcott said. Not a question. Just the word standing alone. Below 6 feet, the ground holds about 38 degrees year-round, regardless of winter cold. Alcott considered this. And the air inside the pipe gets warm from touching the walls of the pipe. Warm enough to cut the heating load by more than half. Alcott looked at him for a long moment. "Samuel," he said, "that is the strangest thing I have heard from you, and you have said some strange things." He was not unkind about it. He simply did not believe it. At the community gathering 2 weeks later at the Harmon settlement store, the reception was less gentle. Samuel laid out the basic principle to the 6 men gathered around the stove and got approximately 30 seconds into the explanation before William Harmon, who owned the store and operated it as his personal forum for community opinion, interrupted. "You're going to heat your cabin by burying a pipe," Harmon said. "Pre-warm the air entering the cabin," Samuel said, "and seal the other infiltration points so all air comes through the pipe." "Pre-warm it," Harmon repeated, with the specific inflection of a man repeating words that he finds inherently amusing. The other men took his cue. Robert Denton, whose farm sat at the top of the hollow, and who had been burning 9 cords a winter for 12 years, said he had never heard of a man beating a Tennessee winter with a clay pipe, and he did not expect to hear of it. "Cut your wood like the rest of us," he said. "That's what works." Thomas Alcott, James's older brother, and a man with less patience than James, said simply that buried pipes were for water and sewage, and he did not understand why a sensible man would confuse one with the other. Samuel walked home in the cold and spent the evening at the table with his journal sketching pipe dimensions. The system Samuel planned required 3 components: an intake structure at the uphill end of his property where outside air entered the pipe system, a buried pipe run of sufficient length at sufficient depth to allow meaningful heat exchange between the air and the surrounding earth, and an outlet point inside the cabin where the pre-warmed air entered the living space in a controlled manner. Site selection for the intake required solving 2 problems simultaneously. The intake needed to be positioned where it would draw clean outdoor air without contamination from the barn, the outhouse, or any other source of organic gases. It also needed to be positioned far enough from the cabin to provide the minimum pipe length his calculations suggested was required for adequate heat exchange. His father's journal, which he had consulted extensively, noted that European installations had used pipe runs between 25 and 60 feet, with longer runs providing greater heat exchange at the cost of greater airflow resistance. Samuel selected an intake point 45 feet uphill from the cabin's north wall, positioned on a slight rise that kept it above the drainage paths that ran down the slope after rain. At this distance, and with the pipe running at a consistent depth of 6 feet, the air would contact approximately 45 feet of earth temperature pipe wall before reaching the cabin. His calculations, based on the pipe diameter he planned to use and the natural air pressure differential between intake and outlet, suggested this would raise incoming air temperature by 28 to 35 degrees Fahrenheit under the coldest conditions. The pipe material was the central technical challenge. Manufactured clay tile pipe of the type used in European installations was not available within 50 miles and would have cost more than Samuel could spend. He solved the problem with a material the hollow had always used for water conveyance. Hollow sections of tulip poplar log, bored through the center with a long iron auger, had been used as primitive water pipes by Appalachian settlers since the earliest days of the region's settlement. A section of poplar log 8 inches in diameter, bored to a 4-inch interior passage, would provide the air conduit he needed. The wood would not corrode in the earth. It would absorb moisture over time and actually improve its seal with the surrounding soil as it swelled. The interior bore, smooth from the auger, would allow air to flow with minimal resistance. He needed 15 sections of 3-foot length to cover the 45-foot run, plus additional sections for the intake chamber and the outlet connection inside the cabin. He spent 3 evenings in November selecting tulip poplar sections from his woodlot, choosing straight-grained pieces without knots that would bore cleanly, and cutting them to length with a cross-cut saw. The boring work took 4 days using an iron pod auger his father had left him, driving it through each section from both ends and meeting in the middle. He tested each completed section by blowing through it and feeling for air resistance on the opposite end. Sections that passed were stacked under the cabin eave. Sections with incomplete bores were reworked or discarded. He connected the individual sections using tapered wooden spigot joints, turning each section end on a simple lathe to create a 2-inch tapered male connector that fitted into the bored end of the next section. He sealed each joint with a mixture of pine pitch and creek clay, heated together over the fire until the pitch melted into the clay and created a flexible, waterproof sealant. Each joint was tested individually before the installation began. The trench digging began on November 28, 1881, and lasted 8 days. Samuel worked alone, which extended the project, but allowed him to maintain the precise depth and slope specifications his design required. The trench ran in a straight line from the intake point downhill to the cabin's north wall, dropping 3 inches of elevation for every 10 feet of horizontal run. This slight downward slope toward the cabin served 2 purposes. It caused any condensation that formed inside the pipe to drain toward the cabin end, where it could be managed rather than pooling at low points in the system. It also created a slight natural draft that assisted air movement through the pipe without mechanical help. The trench depth held consistently at 6 feet below the surface for the full length of the run, except at the intake end, where it shallowed to 4 feet for the final 5 feet before the surface intake structure. At 6 feet depth, Samuel confirmed the soil temperature each morning by pressing his palm against the trench wall. The earth held steady between 38 and 41 degrees Fahrenheit throughout the excavation period, regardless of what the surface temperature did overnight. On the coldest morning of the excavation, when surface air temperature sat at 12 degrees Fahrenheit and the ground surface was frozen to a depth of 8 inches, the trench wall at 6 feet read 39 degrees to his palm. He encountered one significant obstacle at the 30-foot mark, where a large limestone shelf crossed the trench line at a depth that would have forced the pipe run to a shallower depth than his design required. He spent a full day breaking through the limestone with a heavy bar and sledgehammer, removing the pieces with a bucket and rope before the trench could continue at the correct depth. The work cost him 1 broken iron bar and a badly bruised hand. James Alcott walked past the trench on day 5 of the excavation and stopped to look. He stood at the edge for a long moment, looking at the depth and the precise slope, at the care visible in the consistent dimensions. "You're actually doing it," he said. "Said I would," Samuel replied from inside the trench. Alcott looked at the length already completed, the pile of excavated soil beside it, the careful measurement stakes at each end. "I'll come help Saturday," he said. And he did. The pipe installation began on December 8th, with James Alcott present for the first 2 days of the work, lowering the heavy poplar sections into the trench and fitting the tapered joints required 2 sets of hands, one person holding the previous section steady, while the other drove the new section's male connector into the female bore with a wooden mallet. Samuel had constructed a simple wooden alignment guide that held each section at the correct slope angle during fitting, preventing the joints from being driven in crooked. A crooked joint created a constriction in the air passage that would reduce flow and potentially trap condensation. Every joint was checked with a straight rod before the pine pitch sealant was applied. The intake structure at the uphill end was built from flat fieldstone mortared with creek clay, creating a small above-ground chamber measuring 18 inches square and 12 inches high. This chamber protected the pipe opening from direct rain entry and allowed Samuel to fit a wire mesh screen that prevented animals and debris from entering the system. The chamber opening faced slightly downward and away from the prevailing northwest wind, positioned so that wind pressure would not force excessive air through the system during storms while still allowing natural convective flow during calm weather. The outlet connection inside the cabin required the most careful work of the entire project. Samuel cut a 5-inch diameter hole through the north log wall of the cabin at floor level, positioned 8 inches above the finished floor surface. He fitted the final pipe section through this hole and sealed the gap between pipe and log wall with a packed mixture of clay, straw, and pine pitch applied in multiple layers and allowed to cure for 48 hours before the trench was backfilled. Inside the cabin, he fitted a simple wooden damper over the pipe outlet, a sliding panel of hardwood that could be opened to allow airflow or closed to seal the opening completely when outside temperatures rose above the useful range of the system. The damper was the only moving part in the entire installation. He spent the final day of the project sealing every other air infiltration point in the cabin with renewed attention and thoroughness. Every gap between logs was re-chunked with a fresh mixture of clay and horsehair pressed deep into the joint with a wooden tool. Door frame gaps were sealed with wool strips nailed into the frame edges. The window glass was reseated in its frame with pine pitch. The floor joints were packed with clay along the perimeter, where cold air had previously infiltrated from beneath. The total installation, including excavation, pipe fabrication, and infiltration sealing, had taken 19 days of work. Samuel Greer opened the damper for the first time on December 17, 1881. The first night of operation produced results that Samuel had calculated, but had not entirely believed until he experienced them. Outside temperature on the night of December 17th dropped to 8 degrees Fahrenheit by midnight. Samuel had built a modest fire in the stove at dusk, smaller than his usual evening fire, deliberately smaller because he wanted to measure what the system was doing independently of a full fire's contribution. He fed the stove with half his normal fuel load and let it burn down without adding more after 9 in the evening. At midnight, he held his hand over the pipe outlet. The air flowing from it was moving slowly but consistently, driven by the convective pressure difference between the cold outside air and the slightly warmer cabin air. He held his palm in the airstream and felt temperature. Not warm, not cold. The air coming through the pipe was approximately 37 degrees Fahrenheit, as close as he could estimate without an instrument. Outside air at the same moment was 8 degrees. The difference was 29 degrees. Every cubic foot of air entering the cabin through the pipe arrived 29 degrees warmer than it would have through an uncontrolled gap in the wall. And because all other infiltration had been sealed, the pipe was the only air entering the cabin. At 3 in the morning, 6 hours after the stove had last been fed, Samuel measured the cabin interior temperature at chest height, 44 degrees Fahrenheit. On every previous winter night when outside temperature had dropped to 8 degrees, the cabin interior had dropped below 35 degrees within 4 hours of the stove dying down. On this night, it held 9 degrees above what had previously been the floor. She woke at 5 in the morning and said the cabin felt different. Not warm, but different. Less aggressive in its cold. She lay in bed without pulling the second quilt over herself, which she had never done on a December night before. Samuel lay awake until dawn, calculating. January of 1882 delivered the sustained cold that allowed the system to demonstrate its full capability. The temperature in the Appalachian highlands of eastern Tennessee dropped below 0 Fahrenheit on January 4th and stayed there for 14 consecutive days, with the coldest reading of -8 degrees Fahrenheit recorded on January 9th. Wind driven down the hollow from the northwest brought the effective temperature below -25 on the worst nights. The creek froze to a depth of 6 inches. The spring box that supplied the settlement's drinking water froze solid on January 6th and did not reopen until January 19th. Robert Denton, at the top of the hollow, burned through 2 cords of wood in the first 10 days of the cold snap, a rate that would exhaust his supply well before spring if maintained. His family slept in the kitchen, the one room they could keep tolerably warm, abandoning the 2 sleeping rooms to temperatures that dropped below 20 degrees each night. His livestock suffered from inadequate water and reduced feed consumption caused by the effort required to keep the animals watered when every water source was frozen. William Harmon heated the settlement store around the clock during the cold snap to prevent the building's contents from freezing, burning through his winter wood supply at double the normal rate, and calculating by January 10th that he would need to purchase additional wood from the county seat at significant expense before the winter ended. James Alcott, whose cabin was somewhat better sealed than average, having been rebuilt 3 years earlier, managed reasonably well but burned through his wood supply faster than planned and began rationing fuel by the second week of the cold snap, keeping the stove fed only during waking hours and letting the fire die each night. Samuel Greer's fuel consumption during the 14-day cold snap averaged half a cord per week. The pipe system continued operating through the entire cold snap without interruption or adjustment. Ground temperature at 6 feet remained between 37 and 40 degrees Fahrenheit throughout, as measured by Samuel each morning by inserting a thermometer into the intake chamber where he could read the pipe exit temperature before it mixed with the cabin air. Outside air entered the system at temperatures ranging from -8 to +18 degrees Fahrenheit, depending on the night. It exited the pipe at 37 to 40 degrees Fahrenheit regardless. The cabin interior temperature, maintained with a reduced fuel fire burning for 4 hours each evening, held between 52 and 61 degrees Fahrenheit throughout the cold snap. Samuel had never previously maintained those temperatures during a cold snap of that severity under any fuel consumption rate. He was now maintaining them at half the fuel cost of his previous worst cold weather performance. On January 9th, the coldest day of the cold snap, Samuel made a deliberate experiment. He did not light the stove at all. He opened the damper fully at dawn and monitored the cabin temperature through the day without adding any fuel heat whatsoever. By noon, the cabin interior had dropped to 43 degrees Fahrenheit. By 4 in the afternoon, it held at 41 degrees. By 9 in the evening, it had reached its floor at 39 degrees, where it stabilized and held. Outside air at 9 that evening was -6 degrees Fahrenheit. The pipe system alone, with no fire and no fuel of any kind, was maintaining the cabin 45 degrees warmer than the outside air. Samuel recorded this in his journal in his precise, careful handwriting. Then he lit the stove for the evening, fed it 2 small pieces of split oak, and went to bed warm. James Alcott appeared at the Greer cabin on January 14th, the day after the worst of the cold snap broke. He had been rationing his wood for 10 days and had spent those 10 days thinking about the pipe in the trench that he had helped install 6 weeks earlier. Samuel let him in and offered him coffee. Alcott sat down and looked at the stove, which was burning with a low, modest fire. "How much wood have you burned this past 2 weeks?" he asked. "About a cord," Samuel said. Alcott looked at him. "A cord total?" "A cord total." Alcott sat with his coffee for a long moment. "I've burned nearly 3 cords," he said. "And my cabin was cold every morning." Samuel Mulls told him about the January 9th experiment without fuel. He showed Alcott the journal entry with the temperature readings. Alcott read it twice, then set the journal down on the table and looked at the pipe outlet near the floor. The small wooden damper panel, the simple sliding closure that was the only moving part in the entire system. "That's all it is," Alcott said. "That's all it is," Samuel agreed. Robert Denton came 3 days later, riding down the hollow in a way that suggested the visit had been considered and reconsidered several times before he committed to it. He was a proud man, and the gap between what he had said at the Harmon store gathering and what he was now riding toward was not a comfortable one. He did not mention the gathering. He asked to see the pipe outlet and the intake structure. He asked about the pipe material and the joint construction. He asked about the trench depth and the slope. He did not ask about the fuel consumption figures directly, but Samuel told him anyway, showing him the journal with the weekly wood measurements, recorded through October, November, December, and January. Denton looked at the numbers for a long time. "Half what I burn," he said quietly. "Less than half," Samuel said. "In the worst 2 weeks." Denton rode home without saying much more. By February, he had begun boring poplar sections in his workshop. William Harmon came on January 22nd, which surprised Samuel more than any other visit. Harmon was not a man who easily reversed public positions, and his January position at the gathering had been emphatic. He arrived at midday, came inside, and sat down without extended preamble. "Show me how it works," he said. Samuel showed him. Harmon asked sharp, specific questions about dimensions, materials, and construction time. He was clearly calculating labor and material costs as Samuel spoke, running the numbers against whatever he had spent on extra fuel during the cold snap. "How long did the boring take?" he asked. 4 days for 15 sections, Samuel said. Harmon nodded, stood up, thanked Ruth for the coffee, and rode back to his store. He began his installation in the first week of March. By spring of 1882, 4 properties in Greer's Hollow had earth tube air systems either installed or under construction. James Alcott's was finished by February. Robert Denton's was completed in March. William Harmon's store installation, larger and more complex than the residential systems, was finished in April and notably reduced the fuel cost of keeping the store adequately heated through the following winter. The knowledge did not spread dramatically or quickly. It moved the way useful knowledge always moved in isolated mountain communities, slowly, through direct observation and direct conversation between men who had seen the numbers and could not argue with them. No one wrote about it in the county paper. No agricultural journal visited the hollow to document the experiment. Samuel Greer did not present at any gathering or seek recognition for what he had figured out and built. He simply burned less wood. Year after year, winter after winter, his wood pile at the end of each season was larger than any comparable property in the hollow. His left hand hurt less from October through April. Ruth stopped commenting on the morning cold because there was less morning cold to comment on. What Samuel had understood and applied was a principle available to every person who had ever dug a root cellar and noticed that the air inside it was warmer than the air outside. The earth at depth is a thermal reservoir. It holds the average annual temperature of the region. In eastern Tennessee in 1881, that meant approximately 56 degrees at shallow depth, declining to a stable 38 degrees at 6 feet. Air in contact with that earth long enough to exchange heat with it arrives at the other end of the contact fundamentally changed. Not dramatically, Not enough on its own to heat a room to comfortable temperatures, but enough to transform the heating equation from a losing battle against an endless supply of freezing infiltration air into a manageable task of raising moderately tempered air by 15 or 20 degrees. The system Samuel built cost 19 days of labor and materials that existed on any Appalachian mountain farm. It required no ongoing purchases, no fuel, no maintenance beyond an annual inspection of the intake screen and the pipe outlet seal. It operated every winter for as long as the pipe sections held together, which in the case of swelled poplar wood and stable earth was measured not in years, but in decades. The men who had laughed at his buried pipe in November of 1881 were paying extra for cordwood in January of 1882. Some problems look permanent until someone decides to solve them from the ground up. The ground, in Samuel Greer's case, was exactly where the solution was buried. 45 feet of it, 6 feet deep, running straight from the cold mountainside air to the warmest cabin in the hollow.